Now, this is chapter number 3. This is probably the most important chapter that you actually want to pay very close attention to. This is where I'm going to explain you how large language models, also known as LLMs, actually work. If you get this, and you'll have very good understanding of how generative AI works. So please pay close attention to this. So let's understand LLMs. So what are LLMs? LLMs or large language model is a type of artificial neural network that is based on transformer architecture. I'm repeating this. LLM is a type of artificial neural network that is based on transformer architecture. That is, again, transformer is used by only OpenAI and Google. There are now different architectures coming up, but I'm focusing on transformer right now. These LLMs are used to process and generate natural language text, and they are trained on large data set for coherent language generation. Now, if you look at this right side, LLMs can take input of different types of data. They can take input structured data, they can take text data, they can take voice. And on right side, you can see they can perform different functions for you, different tasks for you. They can extract information for you. They can answer questions for you. They can perform sentiment analysis for you. They can translate from one language to another language. They can create computer code for you. There are different tasks that they can perform. So they are very flexible in how they are helpful to us. Now, how do LLMs represent the words? This is important to understand. If you think about humans, us, we represent the words by sequence of letters. So if I think about dog, if somebody tells me, let's say my daughter tells me about a dog, what comes to my mind is a realistic image of a dog in my mind, and also the word dog, D-O-G. When I think of word dog, I think of sequence of letters, D-O-G. That's how I think about it. All humans operate like that. Large language models, on the other hand, they represent the dog or any word in these numbers. You see these numbers? That's how large language models represent the words. Very different from humans. Now you may think, why such complex notation, right? Why would you need to use numbers to represent the words? The closest analogy I could think of to explain this is think of a geographical map. Let's say this is the most simplest geographical map. Let's say there is this place called Portland. That's where our WEX headquarters is. Portland on geographical map is represented by longitude and latitude. Portland has coordinates 43.6 and 70.2. Then another place closer to Portland called Boston that has coordinates 42.3 and 71. Now, if you think about other cities in Europe like Berlin and Paris, they have coordinates 52.5 and 13.4, and Paris has 48.8 and 2.3. Now, if as a human, when I look at this map, I can tell that Portland and Boston are closer to each other than Berlin or Paris. But if I feed this data to computer cannot tell just by looking at it. Computer needs numbers. So computer can, since we provide now coordinates as opposed to names of the cities, computer can also now tell that, hey, the coordinate Boston coordinate 42.3 is very close to 43.6 for Portland. Same as 71 and 70.2. So computer can now determine that Portland and Boston must be closer to each other. But when it looks at the coordinates of Berlin and Paris, which is 52.5, that's far away from 43.6 and 42.3. So it knows now, computer also can tell, hey, Berlin is actually far away from these two cities, of these two places. So that's the concept. That's why computers need numbers, right? So exactly the same concept is used in large language models to represent the words. Now, In large language model, each word corresponds to point in an abstract word space, and I'll show you that how that word space looks like. But in that abstract word space, all words are represented by a number, and those numbers actually determine the relatedness of each word. Meaning, some words are closer to each other, and some words are far away from each other. So if you look at this diagram here, and the word like cat and word like dog, they like cat has a number, but word like cat and dog, they're placed closer to each other. So is word puppy placed closer to dog. Now, since cat and dog could be domestic animals, so they are placed closer to the word house. Um, car can also be found closer to house. Um, man and woman can also be placed closer to house. Hence, they are closer to cat and dog too. Um, Generally, in house, you'll find coffee or tea. So those are also placed closer to house. Um, and generally, people drink coffee and tea. So man and woman are also placed closer to coffee and tea. That's how the words are placed closer to each other. But if you look at the word like tiger, tiger has absolutely nothing to do with coffee or tea. Tiger doesn't drink coffee or tea. So, large language model has placed the word tiger far away from coffee or tea. Now, you may wonder, how did it do that to begin with? You know, by the way, these numbers are called vectors or embeddings, same thing. Embedding is vector list of floating point numbers. That's what embedding is. The distance between these words indicates the relatedness, as I said, right? Now, you may wonder, how did it place those words to begin with, right? Let's take a look at that. The one analogy I can tell you is that when the LLMs were going through the training data, it took a lot of data from all of internet. So it went through a lot of text during the learning. Now let's zone in on these two words, coffee or tea. How did it place these two words closer to each other? I believe what happened is that it came across the phrase, I drank cup of coffee and I drank cup of tea. These two phrases, I drank cup of coffee and I drank cup of tea, millions and millions of times. So during learning process, then I figured out that the LLM figured out that that the word coffee or tea must be closely related to each other, because these two words are always following the phrase I drank cup of. It never experienced I drank cup of tiger, I drank cup of house. Never determined like that, right? It always saw I drank cup of coffee or I drank cup of tea many more times. So then it figured out, since these two words are following this phrase many times, these two words must be closely associated with each other. That's how it created that map of the words. Now, just to show you how this map could look like, here is a map that you see here is of 1,000 most frequent common proper nouns in Wikipedia model. So these are only 1,000 words. It already looks pretty complex. But if you think about the words in the word, there are over 600,000 different words in English dictionary, comprehensive dictionary. But that's just English dictionary. If you think about the specialized vocabulary like technology or chemistry or physics or biology or finance, all these specialized vocabularies have thousands or hundreds of thousands of other words that are not part of the dictionary. So if you combine those uh, specialized vocabularies, these words would be in millions. And if you now do that to all languages in the world, those will go in billions, right? So this map of words would be extremely complex if you think about it. So if you go to this website, projector tensorflow.org, you can actually see the map of words. You can experience it yourself. I would actually recommend you to go that website and take a look at it. But just to show you how that map actually looks like, um, that's only for the word to vec library that I'm showing you right now. But you see, if we focus on this word cellular, it is now, you can see the closely related word is respiration, metabolism, biochemistry, microwave, regulatory, radios. These are the words that are placed around cellular. So just to show you how it places the words closer to each other, and then other words that may not have any association with cellular, they are placed away from each other. So I would recommend you to take a look at this website and then try out yourself what the word map looks like. Now, since now you understand that each word is represented by a number, now let's understand how the LLMs performs calculations on these words to actually come up with answers. And I'm showing you a very simple example here. By the way, these numbers are not as simple. I'm just showing here numbers like 20, 10, 12 to 22 to represent the words. In reality, these words are uh, combination or a set of numbers are pretty large. OpenAI 8 version 2 has 1536 dimensions, meaning each word is represented by 1536 numbers, each word. So these calculations are pretty complex. Now, but to simplify this, let's see, there are four words here. Four words are Tokyo, London, which are capital of Japan and England respectively. So let's say Tokyo has a value of 22, London has value of 20, Japan has value of 12, and England has value of 10. Now, if I take London, which has value of 20, and I subtract the country of that capital, London, which has value of 10. So London was 20. I subtract England from it, which is 20 minus 10, and I add Japan to it, which is value of 12. If I subtract a country from capital and I add another country to it, so that becomes 20 minus 10 plus 12, results into 22, and Tokyo had exactly the value 22, so the answer will be Tokyo. That's how LLMs perform the calculations on the related words. And I'll show you actually more complex example by taking exact one prompt. And I'll walk you through the transformer, how or LLM, how it performs that. So now let's take a real prompt example. Now I'm going to use a prompt on ChatGPT where I'll show you that our prompt is, here is a prompt. Prompt is John wants his bank to cash the. That's the prompt. We'll leave anything empty after the word the, and we'll see what it comes with. And then whatever word that comes up with, I will walk you through step by step. How did he calculate that word? So you'll have good understanding. So let's put that. So let's put prompt that complete the sentence. And the sentence is John wants his bank to cash the. Now I'm going to submit this prompt to ChatGPT and see what it does. So ChatGPT came back with answer, John wants his bank to cash the check. It came with a word called check. Now it's interesting to understand how did it come up with word check after the word the. And that's what we'll dig into. So basically, our prompt was John wants his bank to cash the, and after that space, empty space, it came back with word check. Let's understand how did it do that. So first thing it did, it actually took our prompt, and our prompt was John wants his bank to cash the. For this prompt, what it did, it created vector for each of the prompt. And vector is a set of numbers that I told you early on. Vector looks like this. So for words, say for John, vector would look like this. And it's essentially a set of numbers. As I said, OpenAI's embedding model called Ada version 2 has 1536 dimensions. And what that means is that every word, if you embed it using ADA version 2, is represented by 1526 numbers, like these floating numbers. So first thing it does, it creates these vectors like these for each of these words. Once it does that, then it actually passes on that to a large language model like GPT-4. So from left side, if you see, I was a user. I provided a prompt called John wants his bank cashed to ChatGPT. What ChatGPT did, it actually transformed each of that word into numbers like these and passed on to GPT-4. Now, GPT-4 has many layers of these transformers. There are 120 layers of transformers in GPT-4. So my prompt that I provided, John wants his bank to cash the, went to the transformer number 1 in GPT-4. Now, what did transformer 1 do? Transformer 1, actually, first thing it did, it figured out that the word wants is actually a verb, not noun. Also, same thing for word cash. It figured out that the word cash is actually a verb, not noun. Now, how did it do that? Well, I believe what happened behind the scenes is it looked at the map of words like this. It has a lot of information, right? It located the word John. It probably figured out John is somebody lives in Portland, is married to somebody called Mary, had a cousin called Scott, and both Scott and John have their wants, and this wants is actually a noun. But another word I see closely related in the prompt is called bank. And John, since the word bank is closely associated, the three other words that I see closely associated with word bank are actually verbs. And one verb is withdraw, one is deposit, and one is cash. And the word wants is closely associated usually with verb cash and John than the noun that is wants, because the context here is back and the other verb or wants. So it actually kind of thought that most probably in this case the closely related word here is wants, which is verb, not this noun, and another word called cash, which is closer to the bank, which is verb, than another cash noun, which has one degree or more degree of separation between bank and cash. So then it zoned in on those two words, wants, and it determined that this wants must be the word and this cash must be the verb as well. So at that point, it determined that these two words are not nouns, these two words are verbs. So what it did, it actually overrides the embedding or the numbers for it. It actually assigns the numbers that are assigned to word wants, which is verb, and same thing for word cash. Now, these new numbers are called hidden states. And it took me long time to figure out what is hidden state. Everybody was talking, every article was talking about hidden state, hidden state. I could really not understand what is hidden state, but eventually was able to figure out. Essentially, when the original numbers are overwritten by a new discovery by transformer, then it assigns new numbers to it, and those new numbers are called hidden states. So what it did is overrode that, and then it passed on now all those set of numbers for all the words and these newly written numbers for wants and cash to the next transformer, which is now gone to the transformer 2. Now, what does transformer 2 do? It actually did another important thing. Transformer 2 actually determines that word his is actually referring to this word John and nothing else. Word is not referring to somebody Scott or somebody Peter. It is actually referring to this guy called John here. That's what it figured out. Second thing it figured out that the word bank is actually a financial institution. It's not river bank, because bank can be river bank or financial institution. But it figured that out in this context. The prompt actually is referring toward financial institution by referring to a bank. Now, how did it determine that word his is referring to John? And I will explain that when we go inside the transformer, what exactly happens inside the transformer. So let's take a look at, what happened inside the transformers. But before I go there, now you can see that the first initial layers of transformers are designed to remove any linguistic ambiguities from the prompt. That's what it does. It removes any ambiguities and clarifies what exactly this prompt means to the next set of transformers, so the next set of transformers can do a proper job. Now let's take a look at what exactly happens inside a transformer. Let's take a look at what exactly happened to this. How did we figure out that this word his actually referred to John? So transformer has two important things inside. One is called attention mechanism, and another mechanism is called feed forward. Attention mechanism here. Think of attention mechanism as a matchmaking service for the words. That's what you should think of. Basically, what it does, it creates two distinct vectors for every word in the prompt. So it will create two vectors for John. It will create two vectors for wants. It will create two vectors for word his, bank, to, cash, the, all of these words. It creates two distinct vectors. One vector is called query vector, and one vector is called key vector. The query vector, what it does, query vector actually it defines the characteristics of the word that it is looking for. So in this case, if you look at the query vector of his, the query vector of his is announcing that, hey, I am looking for a word that describes a male person. That's what I'm looking for. And then the key vector for word John is announcing that, hey, my characteristic, I'm a male person. So what attention mechanism does, that across all words, it performs dot product, and dot product of these query vectors and key vectors of all the words will find the match. So then it found the match and it determined that word his and John, his word his is actually referring to John. So that's what attention mechanism did. Now, if you look at the feed forward on the other side, what it does, it relies on the information that it has already learned from internet. So in feed forward network, similar to the calculation that I showed you about Japan, Tokyo, and London and England, is essentially similar concept. What it did at this point, it again looked at the map of the words. It zoned in on the word John that we already talked about, maybe lives in Portland and has cousin called Scott. He probably, in its related map of words, it figured out that John most probably banks up Bank of America or Wells Fargo. I don't know. I'm just, um, predicting that this is how it happened. I could be wrong, but I think most probably this is how it happened. It looked at the word John, it zoned in on the word bank. Now, around the bank, it probably saw the three words that are closely associated with bank, which is a financial institution. Three words are withdraw, deposit, and cash. Now, in the prompt, we saw the word cash, so it ignored these two words because they are not even in prompt, so ignored these two. Let's zone in on cash. What is closely associated with the word cash, which is a word? Generally, people cash either check or they cash money order. But before going there, let me explain that in a calculation. So what it did, it actually took the word bank, which is this one. Then it added the word cash to it, which is the cash verb. Then it subtracted words like money order, which is little away from it compared to check. It said money order doesn't make sense. Although people cash the money order and check, but the frequency of cashing check is much higher than cashing money order. So I'm going to, it had placed the check more closer to it than the money order. So it subtracted the money order. It potentially subtracted the other cash also, because it doesn't make sense to cash the cash. It makes sense to withdraw the cash, not cash the cash. So it added the word cash, which is verb. It subtracted the word money order, and that's how it zoomed in on the word check. That's the answer. And that's how it said, for the prompt that you provided, answer must be the word check. So John wants his bank to cash the check. It predicted the next word. And most probably it predicted that word in layer probably 76 or 85 or 109. I don't know. But you can see that the later part of the words actually focus on grasping the entire meaning of the passage whole, and try to answer the next word for the prompt. And this is not done only for one word, right? It is done for entire sentence after that, or entire passage after that, or entire essay for after that. So these calculations happen pretty fast with GPUs, so you don't feel it, but there are, tremendous amount of calculations that occur on all these words for us to get the answer. Hopefully, this gave you a good perspective on how LLMs actually perform these calculations. But just to summarize, large language models, they are transformer models that are pre-trained on the vast data set, predominantly all of data from internet. This architecture supports hundreds of billions of parameters that enables this model to ingest massive amount of data, massive amount of information, and that is the power of these large language models. Why are they important? They are very flexible. They can perform a lot of different tasks for you, and tasks can be like question answering, summarization, code creation, translating from one language to another language, completing sentences. There are different tasks it can provide, sentiment analysis, classification, a lot of things it can do for you. I'll talk about applications also in demo. And the three core concepts in transformer LLMs are encoder decoder framework, attention mechanism, and transfer learning. We'll learn those concepts in the following chapters. So that was the information about large language models.